Hey guys, I hope all is well. This is going to be a homework help video for section 2.3, and I thought I would take this opportunity to show you an example of a paired test. Because in video 2.5 I showed you proportions and means, but I did not show you an example of a paired test. We saw that option show up in the Data Analysis Toolpak. I'm going to show you how to do it by hand and show you how to do it using the Data Analysis Toolpak using this homework example here. This is from your textbook section 10.3 homework, and number 4, your numbers probably will be different because the red ones are randomly generated. So this problem says, a standardized exam consists of 3 parts: math writing and critical reading. Sample data showing the math and writing scores for a sample of 12 students who took the exam follow. Student, oh, very creative named students here. So we have students 1 through 12. So it looks like our sample size will be 12. These are our test scores. So 2 different sets of test scores. Now, importantly, I already kind of know this is going to be a paired test, because what differentiates this from previous examples we've seen is that the 2 different data sets can clearly be paired by who the student is. Because I know that this student got 540 on the math test and that this student got 474 on the writing test. Since I know the same student took both of those, it makes sense to take the difference between those 2 numbers. But if I'm looking at previous examples like different states, then it doesn't necessarily make sense to pair 2 different states randomly together. So in those cases, I have to use the regular method. And when we have paired tests, we can actually just go back to chapter 9 and simple hypothesis testing, as you guys are going to see in a second. So it says use a 0.05 level of significance and test for a difference between, so that tells us it's going to be a 2-tailed test, right? For the math scores and the population mean for the writing scores. And they're telling us which direction to do the difference, because that will change whether we get a positive or negative number, right? So I'm going to go ahead and copy this data into my handy dandy calculator right here. And it copies over well, thankfully. And then because this is paired data, it makes sense to simply calculate an individual difference between these 2 scores. And I'm being consistent. Notice I'm doing math minus writing, because that's what they told me to do in the problem right here, math score minus writing score. So the first student got 66 points higher on the math score than the writing one. So that's why that makes that's a sensible difference, because we have a matching or pairing variable. This student is called in this case. Now what we're going to be dealing with is an average difference. So here's all of our individual student differences, but we want the average difference. So I can just use the average formula in Excel to get those. Yes, 26 is the average of those numbers. And I wanted you guys to see that I would get the same answer if I took the averages first. And I can just drag this over. I should have just done that in the first place, because I can just drag the formula around, right? So these are the individual averages. Notice that if I take the difference between those, I get 26. So I get the same average difference in either case, whether I take the averages first and take their difference, or if I just take the different individual differences first and take their average. So I just wanted to make that clear that we get the same answer. So that just shows that if we could somehow pair in those other cases, we would still get the same estimate of d bar. So it's really only the standard error that changes in a matched or a paired difference in means test compared to a unpaired or unmatched difference in means tests, which were the types we were doing before. So I'm going to bold these to just, I like to do that to remind myself that these three numbers are not part of the data. So now that I recognize, I can just do a regular hypothesis test on this data, where the null hypothesis is that the difference is just 0. Because we're doing a two-tailed test, null is that it is 0, alternative is that it's not 0 or that there is a difference. So now, because I've been able to create one column of values that makes sense because I have students, I can now just go back to chapter 9 and do a hypothesis test the same way I was doing that. So what do we need? The standard deviation, the sample standard deviation, the sample size. That'll give us the standard error, which will allow us to calculate a t-statistic. And then with that, we'll be able to calculate a p greater than t, because I already see that I'm going to get a positive t-statistic, so I'm going to be looking at the upper tail. I know that because I have a positive average difference right here. But because this is not a one-tailed test, it's a two-tailed test, my p-value is going to end up being 2 times that number. So let's just start applying these formulas in Excel. N is the count of this data, which should be 12. The standard error is, of course, the sample standard deviation divided by the square root of n. I'm using a t-statistic because I had to estimate the standard deviation, right? That's why we're using a t-statistic. I need to take the square root of the, oh no, I don't. I already calculated the standard error. Whoa. So I took the estimated difference. That's kind of like x bar, but now it's a d bar because it's the average difference, minus the null difference, the null mean, but that's 0. So it's really just my estimated difference divided by my standard error to get my t-statistic. What is the probability in the upper tail above that? That's going to be a probability to the right. So I will need a 1 minus t dot distribution. Oops, I need equals in front of this because it's a formula. I want that t-statistic. Degrees of freedom are n minus 1. That's another nice thing about paired tests is that we don't get those crazy degrees of freedom calculations, comma, true. And so that is the area just in the upper tail. But remember, if we're doing a two-tail test, I need the area in both tails outside of my test statistic. So I'll do 2 times this number. And that should be my p-value. Okay, so notice that once we took the differences, notice that that's just one column of data with one sample mean. Then I'm back into my simple hypothesis testing world. So paired tests are pretty easy, actually, because once we recognize we can take the individual differences in that world, then we can just go back to regular hypothesis testing. So let's just check this out. I have the solutions open. There is our t-statistic, 2.458. Here is our p-value, 0.0318. And then they ask you some other questions below. D bar right there, they ask you for that later. But really, we needed to calculate it earlier in the process right there anyway. So there's 26. Now, the other thing I'm going to show you is that the way I would do this in the real world is I would use the Data Analysis Toolpak, because that's just like, we just looked at the underlying machinery of what's really going on and did like every step in the hypothesis test, right? Well, Excel has tools for that if you get this Data Analysis Toolpak. And we saw this last time and I mentioned it. The book calls this matched data. It's often referred to as paired data as well, which is what I usually refer to it as. Before, we didn't get to pick that option because we didn't have paired data. Well, now we do. And so let's go over these options really quickly. We do have paired data now because we have a student pairing variable. What you should think about is, does it make sense to organize my data in a way like by student and then take individual differences? If the answer is yes, then you have paired data. If the answer is no, then it's one of these three types of tests. Now, the difference between T and Z is the same as it was before. You should use Z if you think you know the population standard deviation. Otherwise, you should not use Z. Then you have to make a decision between these two t-tests. Basically, you should always assume unequal variances because that is a more conservative assumption, and we tend to make the relatively conservative assumption in statistics. Unless there's a special reason, like the homework problem tells you, to assume that you have equal ones, then you can use that. But once we use this tool, Excel, so when you open it for the first time in a new Excel session, I think these will all be, I'll try to recreate what it looks like. The alpha is preloaded, so they assume you're going to use an alpha of 0.05. You can always change that. And they usually start like this. So this is how it opens the first time. Well, we have two variables because we're doing a paired two sample for means test, right? Our two variables are math and writing scores. So I'll click in variable 1 range. Excel will take the first number you highlight, variable 1, and subtract the second variable you highlight, if you ever care about order. Or actually, it won't even do that subtraction, but as you'll see in a second, but it will show you the numbers in that order, like your T statistic, for example. Variable 2 range is our writing numbers. Notice that I included labels, so that's why I'd have to click this box, because those aren't numbers, and Excel will get confused if we don't tell it that it has labels in the first row. You should get in the habit of doing that because it's helpful in terms of how Excel shows you the results. And it gets more helpful as what you do gets more complicated. So I would just get in the habit of always choosing labels. So output range is what I always pick. I'll just put it right here. If we click OK, it produces this set of results. Now here's our two individual means that we saw before. 514 for math and 488 for writing. Those are these that we calculated. So it calculates those for you. Annoyingly, it doesn't calculate D bar, which I think is weird and dumb, but there it is, 26. That's our D bar. Observations is 12, you knew that. Pearson correlation is telling us that these scores are correlated. Students that tend to get higher math scores also tend to get higher writing scores because that is a positive number that's close to 1. This is just reminding us our hypothesized mean difference was 0. That's like the null mean or the null hypothesis. Degrees of freedom was 11 because this is a paired test. Using this for unpaired tests is awesome because Excel will produce that number for you using the more calculated formula or the more complicated formula if you're doing an unpaired test. And that's kind of an annoying formula to deal with. Sometimes Excel is 1 off, and you have to decrease this number by 1 to get the right answer in the book. That's because the book always rounds down, and Excel does not. Here's our T statistic, 2.458. There it is when we calculated ourselves. Probability 1-tail, we calculated that when we were on our way to calculating our 2-tail probability, right? So that's right there. We never told Excel whether it was doing a 1-tail or a 2-tail test. So what it does is it just shows us the results for both. So at this point, you just have to decide whether you should be looking at these numbers or these numbers. We should be looking at this number. That's our p-value, as we saw in the book, 0.0318. And now, remember, we did the p-value approach or critical value approach. You can always do that with these results too. P-value approach means compare your p-value to alpha, which is 0.05. So we reject the null hypothesis because this is less than 0.05. Another way to do it is to ask, is our t-statistic farther away from the null hypothesis than the threshold, which is 2.2 in this case? Yes. So that's, again, both lead to the same conclusion. Our t-statistic is greater than the critical value in absolute value terms, so we reject the null hypothesis. Or our p-value is less than the alpha, or significance level, so we reject the null hypothesis. They always lead to the same conclusion because this is just the number and the axis of the distribution, and then alpha is the associated probability with that number, and then this is just the area outside of our t-statistic. So it's good to start thinking about the relationship between those as these distributions are getting more complicated, especially now that we're looking at two different numbers, right? All right, so let me know if you have any questions about that. Good job on everything so far, and I hope to talk to you soon. Bye-bye.